So my name is Mike Ulrey. I used to work at Boeing. I don't anymore. I have a new hobby, and I'm about to show you some of it here. So for my talk, at first I'd like to thank my sponsors. It was a very fortunate circumstance. I don't know if you read this, but the Nobel Prize in Physics was awarded this month, like 2 weeks ago, to these three guys who figure prominently in the kind of thing I'm talking about. So just in case you thought I wasn't going to talk about anything important, this will show you, yeah, indeed, it is important. They're the ones who did some of the first experiments, and the last experiment, Zeilinger in the middle, which verified that, the Bell inequalities are not satisfied in the certain type of experiment. You can read the article in Quantum Magazine, and you can watch a PBS Nova episode called Einstein's Quantum Riddle, which came out in 2019, which is kind of interesting, which shows Zeilinger's very exotic experiment where he used the light from quasars 9.8 billion light years away, or separated by 9.8 billion light years, just to prove that there wasn't any common cause effect to the detector settings. It's a pretty interesting video, pretty interesting show. So overview, question. Does quantum mechanics admit a classical local hidden variables explanation? Context today is a simple EPRB experiment, 2 observers, Alice and Bob, 2 measurements per observer, 2 outcomes per measurements. The historical approach is typically bottom up. You start with classical assumptions, derive an inequality. That's what Bell did, and lots of other people have done. My approach is not terribly different, but I think it's more intuitive, at least to me. It's call it a top-down approach. I spent 4 years studying this and reading, and I wrote a paper which appeared in a journal in the archive. The links are there. You can read that if you're interested in more details. And what I do is start with a completely generic model that includes both quantum mechanics and several classical alternatives as special cases, and then show that the classical alternatives cannot replicate at least some QM statistical predictions. I also show a hierarchical tree where all the classical alternatives stand with respect to QM. I come up with, well, Mathematica, which was my big help all this way, doing visualizations and computations, of course. 3D plots that I've never seen before in the literature of correlations. Some have, some have not. I have an alternative characterization of hidden variables, the classical approach for this, which I think is more intuitive, and the concepts of outcome predictability and measurement predictability. Measurement predictability has to do with faster than light transfer of information. Of course, I show it's impossible, but it's a different kind of proof from the usual one. I'm not going to do that today, but you can read about that last one in the paper. Brief history of Bell's theorem. EPR, Einstein, Podolsky, and Rosen, of course, wrote a famous paper in 1935, not questioning quantum mechanics, but questioning its completeness. Elements of reality, they said, are not really included. You got to get those in there somehow. They had a thought experiment. Einstein and Bohr debated it, and starting in 1935. It sort of just trailed off then. People sort of thought, well, Bohr won these debates, but nobody was really sure. Bell came out with his famous theorem in 1964, coming up with an inequality. He said if classical assumptions must satisfy this inequality, if you have an experiment that can show that they're not satisfied, then you'll probably say there's no classical explanation of this kind for quantum mechanics. And then several experiments were done. Aspects experiment in 1982 was the first one that sort of confirmed this, but there were still loopholes, and that went on and on and on. And in 2018, Zeilinger did his loophole, quote unquote, loophole-free experiment, which apparently closed the case. But anyway, that's the story. Let's talk about the EPRB experiment. This comes from Aspect's paper, this diagram, the whole idea. It's a wonderful paper. It's called Bell's Theorem, the Naive View of an Experimentalist. This is the setup here. I'm not going to talk about the hardware in any detail at all. It's just 2 photons that go not entangled photons that go in 2 different directions. The Alice's lab on the left and Bob's lab on the right. And they measure the polarization. They get out a -1 or a +1. That just means it's bivalent. we'll just call it -1 and +1. And then there's a coincidence monitor that checks whether they both get pluses or minuses, that's sameness, or they get a minus plus or a plus minus, that's differences. So they count the sames and the different ones. And then this is how the statistics are collected and correlations are computed. As I say, Alice gets a plus or minus 1, Bob gets a plus or minus 1. They go into the coincidence monitor, out comes a plus or minus 1. And then they're categorized by bin, 4 bins, 1 bin for each measurement combination. Alice has 2, Bob has 2, so altogether they have 4. So there's 4 bins. Then you compute a correlation for each bin. This is what this is right here. It's the number of positives minus the number of negatives over the sum of the two. And notice that makes sense. If NK minus is 0, that is you got no different ones, you all got same ones, then you're going to get NK plus over NK plus, which is 1, a correlation of 1, just what you'd expect. If you get all minuses, then the NK plus goes away. You're left with minus NK minus over NK minus, which is -1, anti-correlated, perfect. If there's just as many matches or mismatches, then AK plus equals NK minus, you get 0 in the numerator, correlation 0. So that makes sense as a correlation measure. So that's what you're talking about in the experiment, computing the correlations. Then after you get those correlations, you compute these S functions. And now this is aspects notation. He calls these S functions. I'll call them that too. They're basically the sum of the correlations where you put a minus sign in each of the 4 possible places. Then you compare these 4 numbers that you get out, the S functions, to -2 and 2. If they're in between -2 and 2, you say the CHS inequalities are satisfied. And we'll see, as we see, most classical alternatives require these to be satisfied. Quantum mechanics violates them, the theory anyway, and ultimately experiment. You'll notice Clauser, the first name in the CHSH, is the guy, one of the guys who just won the Nobel Prize on my first slide. So he's an important guy. So, and then, as I said, the Zeilinger experiment kind of closed the case on the experiments in 2018. So now I want to talk about how I model it, how I think about it. What I tried to do was mimic what QM does. This is the photon polarization. This is just the classic quantum physics. Well, I shouldn't use classic. This is quantum physics predictions for the outcome, the probabilities of getting a -1, a -1, -1, and 1, given these measurement settings. So there's 16 possible probabilities. This table over here just all this does is emphasize that these are conditional probabilities. Now let's compute the correlations in S functions. This is pretty easy to do. It's straightforward. It's well known. These are the correlations you get. Notice if you do the spin experiment, you get θ1 instead of 2 θ1. It's off by 2, but in the photon polarization, you get 2 times. But anyway, the end result is that the bounds now are not -2 and 2, but you have a multiplicative factor of square root of 2 in there. Those are called the Searleson bounds. Is that how I pronounce it? Anybody know if I'm pronouncing it right? Anyway, I'll call it Searleson bounds. And those are for quantum mechanics. And this is all dependent upon these measurement angles satisfying some linear constraint like this. If you look at the way Alice and Bob's measurements are, and you assume they're coplanar, it's very easy to see geometrically, you have to have a linear relationship between the difference angles. Remember, the thetas are not the measurement angles, but the differences between the measurement angles. Okay, so let's move on to, come on. Sometimes my page down. Why does the page down work? There we go. Okay, what is a model instance? I'm going to talk about model instances a lot in this talk. All I mean by a model instance, I'm going to define some more model types later on. You also already saw the QM model type. A model instance is just where you give it specific values for the parameters. So if you give those values 67.5 degrees, 22.5, and so on, you get these numbers for the conditional probabilities. That's called a model instance. That's what I'm going to mean by a model instance. This is the one, the famous one that maximally deviates from the CHSH inequalities. You get one of these S functions, which is 2 times the square root of 2, which is as big as it can be. So that's a bad one there for classical interpretations. So what I do is I define a generic model type based on the QM idea. I just posit 16 parameters, gamma 1 through gamma 16, but I require that each row in this table sums to 1, because this is going to be one complete probability space based on the context of Bob's analysis measurements. And again, I emphasize that over here, both the conditional probability is explicitly written out. Then the correlations are like this, and the S functions are like this. Now, obviously, each one of these includes all gammas, which sum to 4, and they've got plus or minus signs in there, so they have to be somewhere between -4 and 4. So obviously, some of them will have correlations which are small, some which are too large to satisfy quantum mechanics. So we're going to have all kinds of different models in there. Let's specialize a little. Well, first we need some definitions. Remote context independence means Alice's measurement does not depend upon what Bob's measurement choice is. His can be any of his V or V prime, it doesn't matter. Alice gets the same probability for hers and the same for Bob. In other words, Alice's outcome doesn't depend on Bob's measurement and vice versa. Remote outcome independence means that the joint double probability is equal to the individual outcome probabilities based on their joint measurement. That's what it means to be conditionally independent. It's not a real independence or absolute independence, it's a conditional independence. Factorizability is even stronger. The joint conditional probability is the probability of Alice's outcome given her measurement alone. And that assumes RCI right there. You can't have that without assuming remote outcome independence. So that's implicit. But anyway, this is a very powerful assumption there. As a matter of fact, you can show easily that the factorization condition is equivalent to RCI plus ROI. Non-contextuality is tricky, and I'm going to overstate it a little bit. For the purposes of my paper and the purposes of the presentation, I'm going to say it means that the measurement process consists of definite pre-existing values just waiting to be measured, observed. That's what the measurement process is. That's the really classic idea of an experiment in classical physics. Does it apply to quantum mechanics? We'll see. There are consequences to that assumption. And you can read more about the definition of non-contextuality in the Stanford Encyclopedia. They have a nice discussion there. Okay. Now, outcome determinism, this is something I discovered using Mathematica. I could never have done this without asking it to just do a brute force search. But it turns out that the outcome deterministic model instances fall into several different classes. The most important class are these 16, which satisfy remote context independence. There are others which satisfy CHSH, but not RCI, and 128 of them not only violate CHSH, but even the Searlson bounds. But the important thing are these 16 that satisfy RCI. Those are very crucial. And the reason they're crucial is that these 16, well, first of all, let me show you what they are. These are the 16. The columns show the model instance. I couldn't put 16 tables up here, so I compressed them into columns. The colors differentiate the rows in the standard table. So the first pink is the first row, blue's the second row, green's the third row. You notice no matter which one you choose, there's exactly one 1 in each color and 3 zeros in each color for every model. And that's true for these RCI plus OD model instances. Their correlations, not too surprisingly, are all 1s or -1s. They're perfectly correlated or anti-correlated. All their S functions are 2 and -2. They not only satisfy the CHS inequalities, they meet them exactly. Okay, tight bounds. Now for the non-contextual model type, this is something I've never seen in the literature. I sort of came up with this by other means I can't go into right now. It takes too long to discuss, but anyway, if you start with any probability mass function, that is 16 numbers, non-negative, sum to 1, and you put them in these 4 rows like this, you'll notice there's exactly 1 row K out of the 16 in each row in different orders, but they're all represented in each row, so they must add to 1, since I'm assuming they're a PMF. These are the non-contextual correlations. But the really nice thing, interesting thing is you get a sum and pluses and minuses of the row k's, the 16, all 16, which must be -1, between -1 and +1, obviously, but multiplied by 2, which means that the limits are -2 and +2. So you just did a simple proof of the CHS derivation of the CHSH inequalities for the non-contextual model type. That's trivial proof, and I like that. It's very, very nice. The factorizable model type is one that Bell discussed in his 1976 paper. It was his second paper on this subject, and this has to do with factorizability. I call these conditional probabilities single conditional probabilities that divide up Alice's into alpha-1 through alpha-4 and Bob's into beta-1 through beta-4. They obviously, if you look at them really closely, you see alpha-1 plus alpha-3 has to be equal to 1. Alpha-2 plus alpha-4 has to be equal to 1. Same for the betas. This is what the conditional probabilities look like. This is what the correlations look like. And these are pretty messy S functions. And you could spend some time and prove that those must be between -2 and 2. But there's a much more elegant proof, which I discovered with Mathematica. Again, it's beautiful how it just solved this thing for me. Just define the non-contextual parameters to be equal to these alpha and beta products of 4 alphas, 2 alphas, and 2 betas each. Then use these constraints. Just do a little algebra. You can show that this is a PMF. In other words, these 16 products of 4 numbers add up to 1. Not only that, if you plug them into the table for the non-contextual model type and simplify, you'll come up with this table right here. So a very simple proof that every factorizable model instance is also non-contextual, therefore must satisfy all the CHS inequalities. Finally, the trivial, this is just for completeness. It's completely trivial. Everything is 1/4. Obviously, this is a legal model. Not very interesting, all uniform, no correlations, all 0, S functions all 0. So what? Well, it comes at the bottom of a tree I'm going to show you. Here's all the models all together, just to show you what they look like, divided up by row, showing that by color. If you put it into a 4x4 table, the colors differentiate the rows. And finally, the constraints that make all these into conditional probability vectors. Now, here's the tree I'm talking about. This is interesting because you'll notice I've got red and green boxes except for quantum mechanics, which is the blue box, blue outline. All the red boxes, all the model instances satisfy the CHS inequalities. All the green boxes not only violate the CHS inequalities, but some of the model instances in the green boxes even violate a Searleson bound. So there's nobody else in this whole list, this whole tree, that can replicate quantum mechanics. Either the S functions are too big or the S functions are too small. So you always have something that won't work. Anyway, this is something I've never seen before. It took me, I don't know, a couple of years to figure out all the different cases. And these are all proper inclusions, by the way. The arrows indicate set inclusion. These are all proper. I had to come up with all the counterexamples. Thank God for Mathematica. I'll tell you that. Anyway, here's another view. QM and non-contextuality have a non-empty intersection. There are model instances that are the same. They're both. They're QM and non-contextual. There are QM model instances that are not non-contextual. All the factorizable model instances, the RCI plus OD model instances, are non-contextual. The only model instance also that's QM and also factorizable is a trivial one. That's the only one. Okay. So moving on, the 3 theorems of John Bell. I claim there's 3 theorems, and there's other people who've written papers like this, but I kind of stole some ideas from all of them. But anyway, what the 3 theorems of John Bell, I say hidden variables model cannot replicate at least some of the statistical predictions of QM if it's based on either RCI plus OD, that's his first paper in 64, factorizable, the factorization condition, that's one of his other papers in 76, And noncontextuality, which is his paper in 1966. Actually, he wrote it before he wrote the first paper, but there was an editorial snafu and it didn't get published till 66. But anyway, that's the hierarchy that I'm talking about. Now, here's the plots of correlations that kind of confirm. Here's Bell's 64 paper 76, 66. This is RCI plus OD. These are plots of correlations. I've never seen these QM correlations. You also see this in the literature, these polytopes for the Bell. These are exactly, these blue solids are exactly the Bell CHS inequality, HS inequality, the facets of those inequalities. If you plot them in space, 3D, I mean, you have to fix one. C1 is fixed. -1 in the first column, -1/2 in the second, 0, 1/2, and 1. The other three correlations are allowed to go free based on a constant for that column. And I've never seen these factorizable column plots either. That's new to me. Anyway, thank God for mathematics again. But anyway, you can see the progression of RCI plus OD is a subset of factorizable subset of non-contextuality. Now, these are just correlations. So that doesn't prove the theorems, but that confirms them, visual confirmation, which is kind of nice. What you can prove is that the convex hull, this is a basic theorem. This is my version of the hidden variables theorem that you usually see. The convex hull of all the 16 RCI plus OD model instances equals the set of all NC model instances. In other words, if you take the columns in the table of the RC, the 16 RCI plus outcome deterministic model instances, you combine them with any PMF, the row Ks are non-negative numbers which sum to 1. So this is a convex combination. You get a vector of conditional vector of numbers, which is exactly the list of the non-contextual conditional probabilities. Magic. In other words, non-contextuality and factorizability, this is just a schematic picture. It's meant to be kind of like a convex polygon, and this is the interior of it. The RCI plus OD on the outside is vertexes, non-contextual and factorizable on the inside. Of course, this is just a schematic. It's really a 9-dimensional subspace, a polytope in 9-dimensional subspace of 16-dimensional Euclidean space. And then you can go and take the convex combinations of all OD, 256 outcome deterministic model instances. Guess what? You get all the generic ones, including QM, which would suggest you can make a hidden variables model for quantum mechanics. You can. It's outcome deterministic, but it's not local. It won't be local unless you get inside this intersection here of non-contextuality and quantum mechanics. Then you can do it with a local one, okay? And that's what I show here. Here's the non-contextual one. Angles 135 degrees, 0 degrees, 90 degrees, 45. That's this model right here. That's a QM model. It's also a non-contextual model. You set rho K equals 1/4 for 2, 8, 9, 15, and 0 otherwise. You can also write it, there's an equal sign, as a convex combination of these 4 RCI plus OD model instances, all with weight 1/4, will equal this model over here. So there's a hidden variables model for this QM model instance, but it's not, I'm sorry, yes, it's a local outcome deterministic model, but that's okay because this just happens to be one of the QM models, which is also local, also also a local one, non-contextual, I should say. And you can turn this into a classical hidden variables model. I detail it a little here, but I'm probably running out of time. So let me go to the next one. Here's one which is not contextual. This is the famous one that violates the CHS inequalities. It has a S function equal to 2 times square root of 2, which is bigger than 2. So it cannot be non-contextual because all non-contextual model instances satisfy the CHS inequalities. And this is where Mathematica, just unbelievable, found me these 13 model instances, which are outcome deterministic. They're all 0s and 1s. They go across, by the way. This is one model. This is the second model. This is the third, and so on. And these are the weights that go with them. They're all some cosine function or squared of 67.5 degrees in some combination or another. I never would have found those weights with pen and paper, obviously. Anyway, So this would seem to suggest that there's a deterministic model for quantum mechanics. But what's wrong with these OD models? None of them satisfy remote context independence. They're non-local. So this is a perfectly legitimate outcome deterministic hidden variables model for this QM model instance, but it's not local. So what does this all mean? This is my last slide, a fable. Suppose Alice and Bob ask their friend Eve to try to fool them into think they're receiving data from an EPRB experiment. So Eve sends out 4 numbers, A1, A2, B1, B2. She sends A1 and A2 to Alice. If Alice chooses her first measurement, Alice gets the number A1. If Alice chooses her second measurement, she gets the number A2. Similarly for Bob. So what does what does Eve do? She's got to have some method of sending out. So let's suppose she has a probability distribution. Now, this is not a conditional probability vector. This is a PMF now. Row 1 through row 16 is a PMF. They add up to 1. So she's got, for each of the 16 possible numbers she sends out, she's got some probability. She gives A1 and A2 to Alice, B1 and B2 to Bob. They choose their measurement, they get their output. Now, what happens when you compute the marginals? Let's compute the compatible marginals of that distribution. What are those numbers in there? Those are the non-contextual ones. Those are exactly the non-contextual conditional. If you view these as conditional probabilities, double conditionals, those are the non-contextual conditional probabilities. Therefore, Eve will only be able to fool Alice and Bob if it's a non-contextual model instance, like that first one I showed. If it's the second one, she won't be able to fool them. So what's the conclusion? The conclusion is, my final conclusion, in a QM world in which the behavior can be contextual, it is not always possible to fake the results in a way that ignores future measurements. That's deep stuff. Anyway, that's exactly, sounds a lot like what Bohr was saying, trying to say to Al. Al, baby, you got to wait for the measurement to know what's actually going to happen. And this is kind of what the theory says. And those experiments, like the ones I showed Zeilinger and so on at the beginning, who did those experiments, so far have concluded, and the 2018 one supposedly closed all the loopholes and said, yeah, nature violates the inequalities. Anyway, this is just my way of looking at that situation. I think it's more intuitive than the traditional hidden variables approach, but it comes to the same conclusion, obviously. Anyway, that's it. Thank you.